This is the second part of a makeup video for Stat 401B at Iowa State University, fall semester 2015. It concerns an analysis of some Ames home price data that are in a text file on the Stat 401B homepage. I have put those data into a text file, and now I'm going to uh, copy them to the clipboard and read them into R by doing this. I've already loaded the psych package that will give me simple syntax for using the read.clipboard function in R. And so when I run that, I've created a data I've created a data set called Ames houses. If I wanted to, I could make that into an honest data frame by running the house by running this command that says house is data.frame of Ames house. And I'm going to uh, differentiate between the first column of that data set and columns 2 through 15 by calling the columns 2 through 15 my predictor variables. There are 14 of them, and calling y my variable to be predicted. And so I'm going to call those x and y, and I need them for what follows to be recognizable as matrices. So I'll run these two commands, and now I've got x and y. Now what I'm going to do is I've already loaded the Glimnet package, stats, and graphics packages, and I'm going to do some cross-validations to pick the best lambda values for a lasso regression, a ridge regression, and an elastic net regression. I'm actually using an alpha 0.5 for that elastic net. I could have chosen other alphas, but that's the one that I'm using in this particular demonstration. So the syntax here is cv.glimnet. I need to give Glimnet what the set of predictors is. I need to tell Glimnet what's being predicted, and the value of alpha 1 corresponds to lasso, 0 corresponds to ridge, and the alpha that I'm going to use for the elastic net is 0.5. So if I run those, that goes off and gets calculated. I've created over here I've created objects now that are these Ames lasso, Ames ridge, and Ames elastic net objects. Now, one could ask the question then for the predictors, what alphas do they, what are the best alphas? And this crossvalidation.glimnet has done some calculations, and these are the values that actually are typically used. They're lambda.1 standard error. They're in some sense the largest value of lambda, largest corresponding to simplest predictor, the largest value of lambda that is within one cross-validation standard error of the minimizer of the cross-validation error. And so if I run that, then we see that there are different lambdas associated with with the lasso, with the ridge, and with the elastic net. They're not necessarily comparable, but they got printed out down here in the lower left pane of this R session. I decided that I would do some plotting here. So here is some code that in the first place will put together the lasso predictions, subtract the value of y, use that as a use that as one variable, and then use y as the other variable, and then plot the plot y as a horizontal variable, and this difference between the predicted, the lasso predicted y and the actual y as the vertical variable, and then I'm going to print out what the coefficients are that come from this this lasso fit. So if I run that, then here's what you see. This is y. This is the residual from the lasso fit, and you can see that for large values of y, the lasso is under predicting. For small values of y, lasso is over predicting. If we look at the coefficients for the lasso predictor, we notice that there are a number of them that have been zeroed out, and that's one of the attractive things about lasso, is that it will do its predictions and at the same time sort of do some variable selection for us. So there is the lasso coefficients. I'll do the same thing for the ridge regression. You noticed a slight change in this picture over here as we went from lasso to ridge. You will also notice that in this listing of the coefficients, now there are none of these coefficients that are zero. This is a different circumstance than the lasso. The ridge never zeroes everything, never zeroes something out completely. Then for the elastic net, again we got a small change over here in the case of the y this way and elastic net residual this direction. You'll notice here that there are some zeroed out coefficients in this elastic net. There's not as many as there are for the lasso version, and that's pretty much the way things usually are. The corners of those constraint regions for the lasso are much sharper than they are for the elastic net, and so you'll tend to get more zeroed out coefficients in the elastic net. I did some I ran just an ordinary linear model for purposes of comparison. So I made a linear model of ordinary multiple regression of the home price on the predictor variables and made this kind of a plot for that case as well. And when runs that. Again, there's the plot of residuals versus y, and here now I guess I put together uh, the residuals and the y values that got plotted over here. Now, for purposes of comparing what these uh, methods do in terms of the coefficients they produce and in terms of the predictions they make, I set up some analysis here for making a comparison of the coefficients, and uh, here is a printout that puts them side by side. So down here on the lower part of this, we can see that here are the ordinary least squares, the ordinary multiple regression coefficients. Here are the lasso coefficients. There are substantially fewer of those that are non-zero. Well, there are only 1, 2, 3, 4, 5 predictors in this model. Ridge has all of its variables represented, and the elastic net has some coefficients zeroed out, but not as many as the lasso coefficients. Here's some code for making a comparison of the predictions that come from this kind of methodology. And here's what we get for a scatterplot matrix. I'm going to just look at this briefly and then redo the plotting. But what we've got here are y's, y-hats for ordinary multiple linear regression, y-hats for lasso, y-hats for ridge, y-hats for elastic net. And what we see, for example, well, actually it'll be easier when I show you the next plot. So I added a 45-degree line to that particular plot, and here's what we get. You can see that so this set of, if we look down this column, y is going across this axis and the predictions are going vertically. So if we look at y this way and OLS, or ordinary least squares, that way, we see that we're under predicting a little bit on the high end and maybe over predicting a little bit on the low end, but it's nowhere near as pronounced as it is for lasso, for ridge, and for elastic net. What we're seeing there is that these methods tend to shrink y-hats towards the average of y. They pull them back some. In doing that, they limit the amount of flexibility. They limit the complexity of the predictor, and that's how they gain their advantage on cross-validation error. They do better at predicting off the data set used to fit the models than does ordinary least squares, and the reason is that ordinary least squares tries too hard to follow the extreme values, and these other predictors do not. They don't try nearly as hard. To get an idea or get a better understanding of what this Glimnet program is doing, it's worth coming back over here and examining these Glimnet objects that are made by this call to the uh, uh, cross-validation business in crossvalidation.glimnet. So let's look at Ames lasso, for example, and do some plotting. So let's plot. I'm down here in the lower left corner now. Ames lasso, and see what uh, is going on in this uh, cross-validation fitting. Over here on the right-hand side is a very interesting plot. This is mean squared error. So there is your cross-validation error. And this is the logarithm of lambda. And here is the value of lambda or the value of log lambda that makes the cross-validation error as small as possible. That's not the one that's being used in these fits that I've been showing you. Instead, it's this one. And this one is the uh, uh, the the largest lambda or log lambda that is reasonably close to having this minimum value, meaning that if you go up one, so these bars are are indicating one standard error computed from the folds of cross-validation. And what you can see is that this is right at the level of this is the value where this is the log lambda, where the cross-validation error is not too much above, that is one standard error above this minimum value right there. It's an interesting plot here across the top. What's given are, in the case of the lasso, that's the number of variables that are not zeroed out. It's roughly speaking both for lasso and ridge and elastic net. This is a quote-unquote degrees of freedom, which is roughly speaking the size of the model being fit. So we're talking about a model of size 4 or 5 here is close to the best without pushing all the way over here to 11 in terms of cross-validation error. And that's what we see when we go back over here and look at this list of coefficients. There are 1, 2, 3, 4, 5 of them that are not zero. You can, if you like, you could do similar plotting. Plot with Ames ridge, for example. you get a similar, it's not similar, you get a plot that has a substantially different shape. This is the lambda that's used for uh, ridge regression, and it's based on a model that has 14 predictors in it. And for sake of argument, we might as well look at the plot for Ames elastic net, and that looks much more like the lasso plot, but it has more non-zero coefficients. So a virtue of these fits is that they have better cross-validation error than does the straight up multiple linear regression ordinary least squares. They also have fewer non-zero coefficients, which will tend to make them more interpretable than the full regression model.